A dot B is AB cosine theta. It's the projection of one vector along the other times the length of the other vector. That's scalar multiplication. I mean, scalar product of two vectors, scalar product or dot product. So let's make sure we understand what this equation says. This equation says that for any two vectors, it can be two velocity vectors, it can be two position vectors, it can be a velocity and a position vector, it can be an acceleration force vector, whatever. For any two vectors, the scalar product of those two vectors is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between the two vectors. And what does the cosine between the two vectors mean? Okay, let me say that again with some emphasis. A dot B is the magnitude of the first vector times the magnitude of the second vector. That's what it means when we write the vectors without the vector sign, is those are the magnitudes, positive magnitudes, times the cosine of the angle between the two vectors. So theta, that's a special angle that you need to understand, is the angle between the two vectors. So you may be given two vectors and their angle relative to, let's say, the x-axis. But if we're interested in the scalar product, we need to find the angle between the two vectors. And what does it mean to be the angle between two vectors? We mean the angle between two vectors when they are placed tail to tail, right? So look at this, look at either of these pictures. I'll look at the bottom one, right? We're saying we're putting the two vectors pointing out from the origin. What's the angle between them? The out from some origin, right? The tail to tail. Angle between two vectors when put tail to tail. Which is different than adding vectors, where you have to put them head to tail. Okay? So that's what scalar product is of two vectors. Now, I want to look at scalar product in a different way. We dealing with vector components. Okay, so I've drawn two arbitrary vectors. Instead of calling them A and B, I decided to call them D and J. Why not? And I even gave some numbers just so that one can do this example with numbers or with letters. But the scalar product of these two, I want to know what the scalar product of these two vectors are. And I even made one a force vector and one a displacement vector. It doesn't matter what they are. I said D is a force vector. It's got a magnitude of 3 newtons and its angle is 30 degrees west of south. And J is a displacement vector. Its length is 4 meters and its angle is 20 degrees north of east. Doesn't really matter what those numbers are. I want to find the scalar product. Well, so what's the scalar product of D dot J? D dot J is the length of D times the length of J times the cosine of the angle between D and J. So be careful. I gave one theta D and the other theta J. And theta in this case is going to be the angle between D and J. So we can go ahead and there you go. That's the scalar product in general. But you're right. So in this case, it's the length of D, which is 3 newtons, times the length of J, which is 4 meters, times the cosine of the angle between them. And the question is what is the angle between D and J? The angle between D and J is this main angle here, right? That's the angle between the two vectors. It's always going to be this. If I ask for the angle between the two vectors, you might say, oh, is it that angle? No, it's always the smaller of the two possible angles. There's always two possible angles between the two vectors. One is the angle greater than 180 degrees and one's the angle less than. We want the one less than. So anyway, that angle there is, do some geometry, it's theta D plus 90 degrees plus theta J, right? So it's 20 plus 30 plus 90. So the angle between these two vectors is 20 plus 90 plus 30. Do the geometry of and find that angle there. So that's 140. So it's cosine of. Whoa, hold on. So it's 3 newtons times 4 meters times the cosine of 20 plus 90 plus 30. 3 newtons times 4 meters times the cosine of 140 degrees. It's minus 9.19, and the units are newtons times meters. Don't worry about those units. I just multiplied a force times a distance. It could have been a force times a force. It could have been a velocity times a velocity. It doesn't matter. I just left the units in. So notice that a scalar product can be negative. That a scalar quantity can be negative, right? So a scalar product can be negative. And this one is what it is. It's D times J times the cosine of the angle between them. That's the definition of dot product. Okay, so now I want to ask the question, what if the vectors are given as vector components instead of magnitude direction? Remember, what I gave you was what's called the magnitude and direction form of the two vectors. I gave you the magnitude and the angle. But we can also give vectors in terms of the components. Now what I did here is I just took the components of the two vectors. So I took the component of D Let me just draw it in a different color. Let's do purple. I took the components of D and I took the components of J. So going from the top yellow box to the bottom yellow box, I just took those components and wrote the vectors in component form. And asking, what if I had given the two vectors in component form and I want to know the dot product? We've already calculated it from magnitude direction form, but what about from component form? So pretend we're starting with the component form. So if I want to find D dot J, right, this is just like multiplication, right? D is minus 1.5i minus 2.6j dot, dot j 3.76i plus 1.37j. And when we multiply two things like this, right, we have to do the FOIL method, first, outside, inside, last, right? So we're getting, just like any multiplication, you have minus 1.5i dotted with 3.76i, first outside, minus, so that's the first term, minus FOIL, F-O, outside, I don't know why I'm having trouble with this, minus 1.5i dotted with 1.37j, inside, minus 2.6j dotted with 3.76i, and I didn't leave myself space for last, minus 2.6j dotted with 1.37j. So we've got four terms, right? Minus that, minus that, minus that. Okay, so we've got those four terms. So we now have four dot products that we have to do. Oh my gosh, four dot products that we have to do. Okay, so I just rewrote this on a new page. Again, I didn't leave myself enough room. The only one thing I did here is I just pulled those minus signs into the parentheses just to show that we're actually adding those four terms, and just some of the terms have negatives in them. Okay, so I just rewrote this from the other page, and now I'm just going to go ahead and multiply these out, right? So the numbers just multiply, but the vectors are now the unit vectors, I and j, right? The unit vectors I and j. The vectors multiply out so that we've got, for example, the first term is minus 1.5 times 3.76 times I dot I. And then the second term, right? That's the first term. And then the second term is plus minus 1.5 times 1.37 times I dot j, right? The unit vectors are just vectors, right? They've got direction, magnitude 1, and direction either in the x or y direction. And the third term, right, plus minus 2.6 times 3.76. Whoops, and again, I didn't leave myself enough room, but j dot I. Shoot, let me redo this. Okay, I rewrote that. Those are the four terms where I just took the numbers out from in front of the vectors, I and j. And notice what I'm left with is I can obviously plug into a calculator or do in my head what 1.5 times 3.76 is and 1.5 times 1.37, etc. We can plug those in. But let me just look at the I dot I. What is I dot I? So just as an aside, right? What is I dot I? I dot I equals what? I dot I is two vectors, right? I dot I is two vectors. I dot I, and it's just like any other dot product. It's the magnitude of I times the magnitude of I, magnitude of the first vector times the magnitude of the second vector, times the cosine of the angle between them. So what's the magnitude of vector I? It's a unit vector. It's got magnitude 1. The magnitude of vector I, the second vector, is magnitude 1. And the cosine of the angle between them, what's the angle between I and I? I is a unit vector that points in the x direction. I is a unit vector that points in the x direction. So the angle between those two vectors is what? It's 0. So I dot I is equal to 1. Okay, so what does j dot j equal to? Well, hopefully you can see, since j is a unit vector, j is a unit vector that points in the y direction. It's a unit vector to vector equal to 1. So it's going to be 1 times 1. And j dot j, they both point in the same direction, times the cosine, and the angle between them, it doesn't matter that they are 90 degrees to x, the angle between those two vectors is 0. So j dot j is equal to 1. I dot I is equal to 1, and j dot j is equal to 1. Okay, let me again go to the next page and talk about what is I dot j. Well, I is a unit vector that points in the x direction, and so that has a magnitude of 1. And j is a unit vector that points in the y direction, so that has a magnitude of 1. And the cosine of the angle between them, now there's a 90-degree angle between them. So I dot j is 1 times the cosine of 90 degrees, which is what? That's equal to 0 because the cosine of 90 degrees is equal to 0. And so by the same argument, j dot I must also equal 0. Let me just do a quick aside here. In general, a dot b, which is equal to ab cosine theta, obviously should equal to b dot a, which is equal to ba cosine theta, right? Those are, a dot b is always equal to b dot a. Okay, so just that should be a pretty obvious fact. Okay, so j dot I is equal to 0. So let's go back to this and say, oh, so this term is going to be 0, and this term is going to be 0, and so all we're left with is the I dot I and the j dot j term. So this dot product is equal to, so the dot product of d dot j is minus 5.64 I dot I minus 3.56 j dot j, but I dot I is equal to 1 and j dot j is equal to 1. So this is just equal to minus 5.64 minus 3.56, which is equal to minus 9.2, right? Minus 9.2. Oh, wait, is that what we got before for d dot j? Right, d dot j, remember, when we did it before, we got minus 9.19. Okay, so there's a rounding error here, 9.19 and 9.2, but we got the same result, right? In component form or in magnitude direction form. In component form, it looks a little complicated, but there was some simplification that came, and let me show you what that simplification is. But first, let me just remind you that in magnitude direction form, we're able to say that d dot j was dj cosine theta. We could plug in and find that d dot j is minus 9.19 Newton meters. In component form, we had to multiply out, each of those, right, separate components. So we had 4 terms. But the 2 of the terms went to 0, and it was minus 9.2, and I left off my units. My units are still Newton meters. But in general, let me show you that when we are given a vector in component form, you never need to know the angle, right? We never knew the angle when we were given component form. In general, it's a pretty easy formula. Let's just write that down. So in general, the result is this. It's simple. Right? Look back. All that we ended up doing is we took the x components of the 2 vectors and we multiplied them together, and we added them to the y components. No vectors here, right? It's just the x components, that's a scalar quantity, and the y components, and we added them together. That's what we ended up with when we did this whole long thing, is we ended up by simply taking the x components and multiplying them together, the y components and multiplying them together, and adding those 2 terms together. So when you're given vectors in components, it's very simply take the x components, multiply them together, add them to the y components, multiply together. If there's a z component, it's going to be the z components multiplied together too. And so therefore, right, end result is 2 vectors. And you might not like d and j because those were some arbitrary things. So let me just do, right, so if we have 2 arbitrary vectors, a dot b, final version is equal to ab cosine theta, or it's also equal to a sub x b sub x plus a sub y b sub y. Whoops. It's equal to that. So dot product is, if you're given it in magnitude direction form, you use that one. If you're given it in component form, you use that one. You can always go back and forth between these two. These two are the same thing. So if you know one, you know the other. You can always take components. You can turn your components into magnitudes and angles. But sometimes it's easy just to remember both of these so we can use them in different situations. So I think I've done an example of component form multiplication. I've done an example of magnitude direction form multiplication. And we'll just wait until we apply this to physics problems. This was all math. We'll wait till we apply it to physics problems to do more examples. So have a wonderful night.